So we're live. Hi everyone. We're back with another deep learning session, Portugal. And this time we have with us Luís Rita, who is here to explain us how to use data science to boost sustainable cities. This work is inspired in his startup CycleAI that aims at empowering bicycle riders for their own safety through AI. So you can expect a regular meetup where we have 45 up to 1 hour presentation and 10 to 15 minutes of Q&A afterwards. And if you want your question answered, please write it down on the YouTube chat. That way we can see it and Luis will be able to answer it. Luís Rita is a biomedical engineer currently pursuing his Ph.D. in computational medicine at Imperial College London. He's been writing in towards data science for some time, and he has been named the digital top talent under 25. So thank you very much for joining us, Luís. Here he is. Thank you for accepting this invitation, and yeah, the floor is yours.
Thank you very much, Luis. And that is right. That's me. And I'm right now, as Luis was saying, I'm doing PhD in computational medicine in Imperial. I'm in the second year, and I'm as well the co-founder in CycleAI, along with Miguel Politeiro. And a third element that is also part of the team is Quadrin Bostan. So in that case, Luis, if you don't mind, I'll probably going to start sharing my screen and
Yes.
jump into the presentation.
Mhm.
Can you see my screen? Can all of you see my
Yes.
screen? Okay, great.
Yeah.
So this is our team that I presented at the beginning. We are CycleAI. I'm a data scientist. Miguel is a medical doctor, and Quadrin, web developer. Our motto in CycleAI is to empower bicycle riders to fight for their own safety through AI. At this moment, we count with the support of multiple entities, not only municipalities and Portuguese cities such as Braga, Aveiro, and Lisbon, as well as several non-profitable organizations and organizations that are in favor of promoting the use of cycling and other micromobility means, such as MUBI, the Portuguese Cyclotourism Federation, and the European Cyclist Federation. Along, this is a computational project, so it's highly important to, since the beginning, it was highly important to have the support of multiple tech companies that has been providing us the infrastructure that we need to store our data, to process our data. And I want to mention in specific three of them. I want to mention AWS for the support that has been giving us through the credits that they provided us. Microsoft, which we got recently accepted in their acceleration program in Microsoft for startups, where not only we are having this computational support, but as well the technical support in multiple services that goes through Azure to other platforms that, as a team, they're extremely useful to assure that the work is done as a team and that the sum of the work and that the work of the team is way more than the individual sum of each one of our work, but simultaneously to Vodafone. Getting accepted in Vodafone Power Lab, a branch of Vodafone in Portugal, also has been revealing extremely helpful for us again on the computational from the computational point of view. So as I was saying, our motto is to empower bicycle riders to fight for their own safety. And the way that this project started was Miguel Politeiro, one of the co-founders, had a bicycle accident more or less 2 years ago. I had a master's project that I finished more or less two years ago. And when Miguel knew about my master's project, he contacted me, and once he told me about his situation, and he was as well aware about that I was already working in the past from half a year already in this project that at the time was focused in the city of London, but whose methodology is easily scalable to any part of the world. So, so one of us with a problem, the other with a solution. We got together and we started CycleAI. This is to give you some context about the importance of the problem that we are tackling. Um, having There are 2,000 people killed per year in the European Union, and hundreds of thousands of people every year are seriously injured in the same area. And these numbers will only get bigger if we not only consider this area, European Union, but if we think at the global scale. And having people cycling has many benefits, and one of them is in the environmental perspective. Having more people cycling means reducing the emission of greenhouse gases to the atmosphere, because that means less vehicles using combustion means. And at the same time, there is these environmentally benefits. There is also health benefits, because cycling promotes more active lifestyles, and having more active lifestyles is known to reduce a very broad range of chronic diseases, for instance. But most of the accidents as well that happen in our roads are have cars and other vehicles involved. So this means that reducing the number of cars, trucks, and other similar vehicles in our roads means that we are also contributing to road safety. And the best way to have more people cycling so that we can tackle these three issues, environmental, health, and road safety, is, we believe, was to increase safety of cyclists, safety of the people who already cycle, and increase safety for those as well that are still not cycle, but we want to promote this new way of transport among them. This new way of transport is not the exact term, because cycling is already around for hundreds of years, but this new way of transport, it is becoming more and more used worldwide because of these benefits. And now I'm going to go through exactly how we are empowering bicycle riders. What has been our approach? So in order to empower bicycle riders, we are running two crowdsource models in our website. One that is the hotspot map, and the other that is the perception pool. In the hotspot map, what we ask users is to point in a map places they have passed by that they consider of higher risk. So we ask them not only to provide us the exact location where they found a place to be risky, but as well a small description, and if possible an image of that same place. We have already gathered more than 100 places spread mostly in Portugal, but also abroad. The second crowdsource model is the perception pool. We show users two images, and the question that we make is which one of these images looks safer, the one on the left, the one on the right, or in the case that the user thinks they are approximately the same, it's also a possible answer. And with this data, the data that we got from dangerous points that were manually inserted, and data that we got from these images, what we did was we created a neural network that is able to, based in one image, to retrieve a safety score for that image. So we use the hotspot map as a way to validate the neural network, to check whether the points that were manually inserted were identified by our model. And on the other side, we use the perception pool to train this neural network. But we didn't use the data that we got from the votes from people immediately in the neural network. So what we did was, for every single of the 10,000 images that we are showing in pairs in the perception pool, we detect the objects and the structures that were present. And you have an example in this slide about what type of detection I'm talking about. Object detection, it aims essentially to tell the size and the location and the class of the object that is in the image. And in these images, you can see some of the most relevant objects in our scope, which are the presence of cars, buses, people, motorcycles, etc. On the other side, we used another class of algorithms that is called image segmentation. And in the case of the image segmentation, we can not only infer the size, relative size, we can infer the presence or not in the image, the location in the image, but very importantly, the shape of the object as well. And what we did was, after having the votes that we got from these pairs of images, 10,000 images in our perception pool, after running what are the objects and structures identifying in each one of these images, what we did after was a ranking of every single of the 10,000 images based in the user's votes. So at the end of the day, we got on the top of our ranking the image that were considered the safest by the user, and on the bottom of this ranking, the image that was considered the unsafest. And the way that this ranking was done is not, you cannot use the votes directly and build a ranking to these images, because at the end of the day, this is an optimization problem. Because for some people, they will say that this image is considered safer than the other, but for other people, they will say exactly the opposite. So this means that we have to use an algorithm, an optimization algorithm, and the one that we used was TrueSkill. And what it does is a ranking. It's part of a class of algorithms that are called ranking algorithms, and it's very similar to the algorithms that are used in the games. And the way that it works is we can imagine that each image is a different player, and two players are playing against each other. And if one wins, if one image is considered safer than the other, so that image will go higher in the ranking. And by this, like by having these many matches, let's say, the images will get to a final position in this ranking of the 10,000 images after the multiple matches, after the multiple votes that we got from multiple people. At the end of the day, what we get is a ranked list of 10,000 images, each one with an average score and a standard deviation. A standard deviation that is not that it is as low as more votes that image was involved, and as less the score, as little the score, as safer it was considered by the users. And now here I show you what were the most common classes of objects and structures that were identified through after running our object detection image segmentation algorithms. So from, as expected, the most common objects that we found in our images were cars, people, truck, motorcycles, bus, potted plants, stop signs, benches, traffic lights, chairs, bicycles, trains, and fire hydrants. And on the other side, for the image segmentation, most this scale, on one side, the y-axis of the object detection tells us the number of objects that were identified. The y-axis for the image segmentation on the image segmentation side tells us how many pixels in these 10,000 images were labeled in as belonging to this class. So we have approximately 90 million pixels labeled as sky, less off-road, building, vegetation, car, sidewalk, terrain, wall, fence, and parking. The algorithms that we used for detecting the objects was YOLO version 5, and for image segmentation, it is some that are currently being used by Tesla in their vehicles that belong to NVIDIA. Um, the data sets that were used to train these same algorithms to detect each one of these classes were COCO in the case of the first one, and in the case of the second one was cityscapes. In the case of the first one, there is 80 classes, 80 different classes, although from these 80 different classes, only um, much small number it's of our interest, because for instance, we are mostly interested about objects that can be detected outdoors, not indoors. And in the case of the image segmentation, most of the classes, they are actually classes that are the biggest majority that are relevant to us. On the object detection side and in the image segmentation side, we used algorithms that are available in that are open source, and you can easily find in platforms such as GitHub. So to make to sum up what I said until now was we run these two crowdsourced models, hotspot map and perception pool. Hotspot map to validate this neural network that based in one image is able to retrieve a safety score for the image. And we use perception pool to train the neural network. The way that we did the training was we we after getting the votes from multiple pairs of images, we we run through skill and we get a ranked list of 100 of 10,000 images. We went detecting what were the objects and the structures in those images. For the objects, we consider their number, only their number. For the segmentation for the structures, we consider their number of pixels for each class. For our neural network, we train simple architecture, a sequential model using TensorFlow, and but before going probably to the implementation of the neural network, I think it's very important to talk about some of the filtering that we needed to do from the perception pool, because as expected, we we had plenty of votes that were not real people doing them, and or if because of the time between votes, or even if it was real people involved in these votes, they were not meaningful votes. So this means that before using the votes that I got in the perception poll and the running through skill and getting a ranked list for the 10,000 images, we need to run we need to do several filtering steps, um, based, for example, on the time between votes, and in some other information that we use to infer as the best that we could to tell whether who did this vote is a person who, or if it is not, whether if it is a person, whether this was like a random vote or not. So this was some of the filtering that we needed to make. At the end of the day, after having all this data ready for training, we didn't train straight away sequential model and a neural network. We used at the beginning more simple model and SVM, support vector machine. And at the beginning, we only consider the objects in those images. Only after we consider the objects and the structures in those images, because we saw how that improved the accuracy of detection. So the training was done on one side with the information of the objects and structures in the images. On the other side, we had this one score for each one of the images of the perception pool. So what we wanted to make was like creating a model that based in the number of objects, of different objects and structures in this image, try to predict from that point a safety score. So this means that the input of the neural network, I was saying it at the beginning to simplify, is not an image, but is the information of the elements in those images simplified. Number of objects for each one of the classes, and number of pixels for each one of the classes. We obviously divided our data set in validation, testing, and training, because we don't consider to have such a big data set for the problem that we are trying to solve 10,000. We allocate to 80% of the data for training, and the remaining 10%, and for the remaining 20% for validation and testing. And one way that you can see how we used to validate our model was exactly based in this set of data that was not used for training. We saw for these many images, we saw on one side what were the predictions of the model, and on the other side we had this ground truth. We had a safety score that was given by each image that we retrieved after getting the votes from the perception pool and running through skill. So, and that's what you can see on the bottom of this PowerPoint. One line tells us in the x-axis you have votes that were made. On the x-axis you have multiple images side by side with the respective safety scores associated. The other line that is colored differently tells us what were the prediction of our model. And as closer together are these two lines, the blue line and green line, means that as closer together is our predicted scores to the ground truth scores that we got after running through skill in the votes that we got in the perception pool from the pairs that we show of images from this data set of 10,000 images. And at the beginning, we're only using images from Lisbon, but that's a limitative approach because there is objects, there could be objects and structures that can be present in Lisbon that might not be in London, for example, or the other way around. So in order to build a model that accounts for the biggest range possible of different objects and structures, we not only show the images of Lisbon, but we also show the images of London to build these ratings to get these votes for each one of the images. And this is a crucial part because training neural network implies not only having high quality data, but simultaneously having more data and good data. So, and this is what I depict in this slide. On the left, you can see some of the stats that we have for our perception, for our hotspot map. We got points already in that were manually inserted by people in Portugal, Romania, Germany, United Kingdom, Belgium, France, Spain, Poland, and Ireland. We got not only points identified in these countries, but as well one thing that we allow is for people to upvote each one of these points that were placed in the map. So if there is a point that someone found dangerous as well, that person doesn't have to insert a new one, can just upvote an existing one. So at this moment, we have more than 500 upvotes. This slide is not the most up to date. And on the other side, we have the perception pool. And we got votes in the perception pool from people already in more than 50 countries. And we got votes from more than 5,000 people, more than 100,000 votes. So this means that the same group of people voted multiple times. But again, a very important point here to highlight is again the variability of the data. Not only we are getting the perception of safety from people in Portugal mostly, but we are getting the perception of safety from people in England, Germany, Spain, Romania, Brazil, Belgium, France, Netherlands, Greece. And if I was showing here all countries, there will be more than 50. So at the end of the day, what this means is that there is for sure that parts of the perception of safety in the cycling perspective are different. Some people will consider something to be highly correlated with safety, and some others will tell that this factor is highly uncorrelated with unsafe situations. But when you start growing the amount of data that you have, these votes in the perception poll, you start realizing that the perception of safety starts converging to a unified perspective of safety. So at the end of the day, there's like a core of features in the images, in the surroundings that people unanimously tend to consider safe and unsafe. And these from the in the objects point of view, the presence of bicycles and people in the images were considered to be safe, where there is almost 500% and 33% more of these objects compared with the average in the entire data set of the 10,000 images. On the other side, in the and on the and here we consider the safest images, the top 50 images from the 10,000. So this means that in these top 50 classified images from the total of 10,000, there is on average 500% more bicycles and 33% more people than in the entire data set. And the same way that we consider the safest images to be the top 50, we consider the unsafe to be the bottom 50. And there is absolutely no bicycles in the images that were considered unsafe, and a much less number of pedestrians, people in those unsafe images as well. On the other side of the spectrum, you have trucks and buses contributing from the people's perception of safety to what unsafe is. Going from the object detection to the image segmentation, on the top of the list, the presence of bicycle lanes are the most important factor that people consider safe. So this means, again, in the top 50 images from the ranked list of 10,000, there is in average 380% more pixels from bicycle lanes than the entire data set. And the same applies, the same positive measure applies to pedestrian areas, sidewalks, streetlights, vegetation, and on the opposite side, the presence of buildings, guardrails, bridges, and rail tracks were on the bottom of the list as one of the structures that people consider the most unsafe. So at the end of the day, our approach has this pipeline of having the crowdsources, we do the votes, and then we run object detection, image segmentation. But leaving this part aside, what I wanted to tell is that if there is a new image that was not part of our crowdsources, now we can analyze it. And that is the main advantage of having our own neural network. We don't have any more to ask for more votes for pairs of images, although if we ask, we'll only improve the accuracy of our model if the data has quality. But in principle, now we can, based in one image, we run object detection, image segmentation. We know how many objects of each class, how many pixels of each class do we have in the image. We input that in the neural network and we retrieve a safety score for that image. You have examples here from images that were given very small safety scores. As smaller these safety scores, as more dangerous. And some other images, for example, the one on the right has a cycle lane, were considered the safest by our neural network. And our approach is highly scalable because we use images. And this means that one source of images that we can use because of the API that is available is Google Street View. So you can retrieve several thousands of images for free from Google Street View API, from Google API, although there is a limited amount that you can do it. But having such a source of images that we know that in Portugal, United Kingdom, in most of the European and most developed world countries, this is a tool that is widely available. This means that we could create safety maps. So at the end of the day, what we did is that we were interested about analyzing Lisbon area. We randomly picked 200, 2,500 points from Lisbon, latitude and longitude. And for each one of these points, we analyzed the respective 360 degrees. And this is a crucial point because it's not just analyzing what's happening north, south, east, or west, because if you're facing a specific direction, a cycle lane might be there, but on the opposite one, there might not be a cycle lane at all. So what we did was we ran with our neural network in each one of the 4 images that we got per point, we got a safety score. We averaged the safety score from the 4 images that we have per point, and we got a safety score for that point. As small the safety score, as more dangerous the point, red points, as higher the score, as safest the points, green points. But at, at this moment, we have a map that doesn't still doesn't have the resolution that we are aiming for. We have a map with 2,500 points. We want to build a map for Lisbon and for other cities after, with a resolution in the order of tens of meters distance between points, tens of meters. This means that we want to build a continuous map of safety where from every single point you can see the next one that is closer by, without reducing as much as possible these black spots, areas that can't be seen from one point to another. And that's why we are considering, based in the Lisbon's area, we want, and considering that analyzing a specific point, you can, with the respective 4 images in each one of the 4 angles, you can have a field of view that goes up until some tens of meters, 20, 30 meters. It was based in this hypothesis that we decided to use 250 points, and this means 1 million images, 4 images per point. And that's what we are heading now, creating a higher map of resolution for the city of Lisbon. And right after, the goal will be to scale it abroad to London. But we didn't stop here. We identified the highest, the most dangerous areas for cycling, and also the safest ones. But focusing the unsafe, we didn't stop here. We developed a route planner that not only is able to account for the presence of cycle lanes, in this case in Lisbon, it's able to account for the distance between points, the time of traveling using bicycles between points, but as well avoiding the points that we consider unsafe. You have a QR code in this slide that you can scan, and you'll be redirected to our route planner. And you will, if you do it now or later, you'll be able to see the product that we have been working on. Basically, you insert your destination, where you want to go. You can optionally select from your current location, or put a specific address that you might be interested in starting your journey. And we build a simplified navigation experience in this web app that updates your position in the map while you move, and at the same time is able to tell your orientation, your geographical orientation, but see how, while you move, how you progress in the safest route that calculated for you. So as part of the features of this app that we developed, you can the most important one that I wanted to highlight is actually to, on one side, you can consider every single point that we consider unsafe. And in this scope, we consider unsafe all the points that have a safety score below 5. So if you want, you can calculate routes. that consider that you say I want to avoid every single point that was classified with a score of 5 or below. You can say that you want the fastest route as well. That in that case, it will only consider that only the really dangerous points in the fastest option available in the web app will be considered. At, at, up until this point, I told you these two options. So we either provide the fastest routes, the last one only considers the most unsafe points. Either on the other side, you consider the safest routes, considers every single point that had a score 5 or below. We also had a balanced option that, from our perspective, has the one with the most potential because it's simultaneously able to account for safety, time, and distance. And this is quite new what you are seeing here, because if you most of the route planners that are being used in Google Maps and other apps, they allow you to specify that you want to pass by this place, but they don't allow you to specify that I want to avoid this place. And one of the most important things of CycleAI and how we are different from the other route planners and in general from the other route planners outside is we only use open source tools in our project. We use object detection ULV5 that is open source. We used for image segmentation an NVIDIA algorithm that is open source. And right now we used route planning technology, JavaScript API that is itself open source as well. The API is called Open Route Service, and it allows you to specify as in the coordinates field starting and endpoint. It allows you to specify what type of way of transport are you using and that you want to have the route calculated, driving, cycling, walking, etc. But most importantly, this API allows you to specify the areas that you want to avoid. And the areas that you want to avoid, they can either be specified as with multiple shapes. In our case, we started by saying considering each unsafe point as a square. And in that case, we would say to the API, we want a route not to be overlapped with this square, with the latitude and longitude for each one of the 4 vertices. Right now, we are considering instead of square circles for, but it's the approach the approach is similar. And this is not the only solution that we have. So on one side, we build a neural network that after having the images segmented and processed with object detection, you can retrieve a safety score. Using Google Street View, we build safety maps for Lisbon. And based in our route planner, we can tell people the best way between 2 points, also considering for safety. The way that we are going to monetize our approach is pay per click. So what's going to happen is that this week we are integrating in one of the biggest micromobility companies. It's going to start displaying a banner that's going to start redirecting their users to our website, to our route planner, and having their routes calculated. This means that at the beginning there will be a trial assessing how good our approach is performing, but simultaneously assessing the interest of people. But once we move from this experimental test, from this pilot test, to a more solidified solution, the method that we are going to make our client to pay for our solution will be through this external app. And each time our link is clicked in that app and redirected to our website, a small amount will be charged to the company. So on one side, we have this B to B to C approach, whether there, because there is like an intermediate that is another company, and on the other side we have this B2G approach, business to government, where we provide it directly our safety maps, and we tell these are the unsafest points. If you are planning to buy, if you are planning to build new cycling infrastructure, we can help you prioritizing what are the places that needs the most based in the unsafe points that we have detected in the areas that you are considering to build new cycling infrastructure. And the way that we are going to ask for it is a payment per point that is analyzed. As higher resolution maps, people, municipalities will be interested about, as bigger it will be the price. And so we have these two methods. We are targeting B to B2C and B2G. The problem is that it's not just images um, have a limitation that doesn't allow to capture dynamic factors. So for example, if you are cycling, riding a bike, this means that a car, for example, can just like come in front of us or on the back, even more importantly, that we cannot see. And considering Google Street View images will not tell us absolutely any information, because sometimes they they are static, first of all, and sometimes they are not weekly or even monthly updated. So that's why we complement our solution with this assisted driving approach, an approach that we developed. You have on the biggest video shows you the perspective that you have after placing our prototype, CycleAI prototype, in your bikes or other micromobility devices, vehicles, and it shows you object detection happening in real time. And in this case, in our case, we can not only tell what are the objects, we can tell what's the certainty that we have that those objects are around the user, but simultaneously tell how far they are from the user. And this is very important in the to be able to process this data and letting the user know through light and sound feedback what's happening in front of him, but most importantly on the back. And that's why what we are developing is this prototype that you place in bikes and other micromobility vehicles that tells users based in light and sound feedback what's happening in front and on the back. And if there is a car, for example, approaching on the back, in that case, what's going to happen is that the light or a sound is going to be triggered, and the user will know that he is in risk. The problem is that in cars, because they are bulky and they are expensive, you can easily place their hardware that is heavy and bulky and expensive. But in the case of bicycles and scooters, because they are very lightweight and because they are by themselves already cheap, you cannot just place a extremely powerful GPU that is required to detect the objects in those images. So what we did was that we are leveraging 5G, having a 5G in our prototype, at the same time using cloud computing, AWS, more recently Microsoft Azure, to process the data in the cloud, the video in the cloud, and sending back to the prototype the objects that are in the surroundings. And this is a very, 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 very important way that we found to overcome this limitation that images have. And before moving to the next steps that we are planning, I just wanted to give you a timeline of the project. So we start working on it in October 2020. The crowdsources were the first thing that we start working on. They were launched a few months later in January 2021. Bikeable, the neural network, was implemented a few months later. We were incubated for a few months in a startup Lisbon, accelerated by EIT. In the meantime, we have participated in many conferences, namely Velocity, Web Summit. Now I'm having pleasure of presenting in the deep learning session, Lisbon sessions, our project and the computer vision algorithms behind. In October 2021, we released the prototype that I was talking to you in the last slide in Aveiro. And right now we are involved in we are about to launch this trial with the micromobility company that I was talking to you about, and we are starting multiple collaborations with the municipalities, but as well as universities, where we envision to explore these two approaches, B2B to C, as well B2G, where the municipalities play a central role, but as well as like getting the academia on board, because we not only want to use the tools that are already developed that are out there, but we want as well to build our own tools and to push forward um, the ones that are being used for road safety. At the end of the day, our approach is heavily based in machine learning, more specifically deep learning. Data science is one of the core parts of the team, and I show to you what we developed in the past, what we are working on the present, and now I'm showing you what's the future looks like. And we not only want to consider Google Street View images, they have they are up they have many benefits. As I said, um, they are you have Google Street View in so many places around the world, and in some of those places they are updated very often still in a matter of weeks or few months. But there is this downside that we are trying to tackle with the prototype, that you cannot see in real time what's happening. And but in order to complement, because Google Street View images, they give us like an astonishing space resolution. We can see objects in the images that are only a few centimeters. But the problem is that they are not updated frequently. And until having lots of bicycle riders using our prototype on the roads, we need a way to be able to calculate safety in our roads, but with more up-to-date data. So this means that we are leveraging another solution, that we are considering now only Google Street View images, but with very high spatial resolution. But now we need to have time resolution. And it's exactly for that reason that we will start using satellite imagery. There's also an API available within the European Space Agency in the Copernicus mission, that we can extract images with very high resolution. And that is going to, hopefully, we believe it's going to give us the time resolution that at the moment is missing, because we are considering static images in Google Street View. And I believe that is the combination of both that will be able to create not safety maps like we have now, but dynamic safety maps that evolve in a scale of hours. That's the updating time rate of this satellite imagery. And I think at the end of the day, what I wanted to talk to you about, I think that was it. So I'm now totally open for any questions that you might have, and I will happily answer all of them. Thank you very much, guys.
Thank you, Luis. Yeah, we already have some questions. So, yeah, let's start by this one. How big was your training set? How many user reports? Well, you already answered mostly it, I would say. Yes, exactly. So, was
So
that enough?
we had 5,000 people voting, 100,000 votes for 10,000 images. So this means on average we had 10 votes per image, and we did based in previous studies that were done before. How many images do you want to have ranked? How many users do you need voting? How many votes do you need? And based in previous data from studies that were made with similar approach, but with different scope, not cycling, we target having between 10 and 20 votes per image of those 10,000.
Okay, okay, cool. Um, I'll I have here another question by
Yeah.
Andre. Um, he's curious about the user labeling. So you were saying about um, the pool, yeah, this data that you asked users to label, and you said that you need to clean some way. Um, I think Andre would like you to elaborate a bit more on this, if you would.
Yeah, for sure. So we run two important cleaning steps, because we never know if there is someone that will just go to our website and start voting, making 1,000 votes in the same direction and 1,000 votes in the opposite direction, or just alternating ones. And I have to tell you that this happened. There is, I for me, it's very hard to understand how someone can try to like decrease the quality of your data set in a social impact project where the people that are behind are not profiting a single euro with it, but there is actually people that try to decrease the quality of our data set, but through the time filtering, time between votes, and after filtering the votes as well, based on left, right, middle votes, based on the type on the time on the timing of the votes, and based on the type of the votes, um, we we reduced to half, I think, the the good quality votes. We had, I think, approximately 100,000 that were discarded.
Hmm. Okay, okay. So one question I had is like, you didn't provide any reward to those people, or you didn't
That's
ask,
that's
and
that's a very good point. That's a very good point because one thing
yeah,
that we did was we gamified the experience. So what we did was that at the bottom, after you placing your first vote, it will appear you are in the top 60 of best voters. And then as you keep voting, this percentage is going to get slower and slower and lower and lower and lower until that you are the best voter of our solution. But this is as far as it went. That was
okay,
the only
yeah,
reward that we gave, and based on the people that we managed to put together through our social media as well, that was extremely important,
hmm,
and we managed to get the votes that we needed.
okay, okay. So gamification helped
Exactly,
in collecting the data. Yeah.
but no
So
like no monetary reward
yeah,
we were given at all.
yeah, it's a great idea. We have another question from NL, that is, those images that people were classifying were gathered from cars or bikes, because this might have an
So
impact on, yeah.
that's for sure. These images that were provided, so these images are Google Street View images, and that's true that Microsoft they have their own images, and Apple they have their own images. But for in all these cases, the images from the roads they are mostly taken from the cars that sometimes we see driving around.
Okay,
So you can tell me um, it would be better having um, photos that capture images that capture exactly what would be the perspective of cyclists. I would answer yes. But if you ask me whether this stopped us from building our neural network and having it working, identifying the safest and unsafe images, I don't think is that a big problem.
yeah. um this is another question that you already tackled, that is from Andre again, um that is concerned to the temporary risks that appear in Google Street, and you want to discard them, or you don't want to have them um, like poisoning your data in some way. Um, so the question is how you get around the fact that some image might have been taken when some temporary risk, like a car, was present, but which is not part of the basal background.
So one thing that I have to highlight is that this approach is extremely useful if you consider if you focus in infrastructure, because infrastructure in the roads is something that doesn't change at a weekly basis, not even sometimes at a monthly basis, and that's the updating rate of those images. So infrastructure based in what is the infrastructure in public roads, I think our approach is the best on telling you what are dangerous and the unsafe, the dangerous and the less and the safest places.
Yeah, yeah,
And at the end of the day, that is true. For example, it can happen that um, for example, imagine that there is this car that is getting the images for Google Street View. In front of him, there is another car. So this means that the image in that angle, most of it will be covered by another car in front of it, and hardly something else might be seen. But there is three other angles, and if at the end of the day we consider the scores that we get from 360 degrees of that point, although those are dynamic factors, presence of cars there or not, if you average through 360 degrees the position or the data point that you are considering, I think this problem becomes less of a problem. Um, and there is a study out there that says that although you cannot capture Google Street View images, what are dynamic factors, right? Because they vary over time. You can have a very nice, you can still extract good information about what is the average at some events are happening. For example, if in some images from a specific road you see many cars, this means that although you cannot tell that this is the road, uh, although you cannot have like this time frame very well established that this is happening today but couldn't be happening tomorrow, it still gives us a good overview about on average what we can expect from the place. So that's what I wanted to highlight. Considering the 360 degrees per angle reduces that uncertainty of having a car, for example, in one of the angles very close and nothing else is seen besides that. And simultaneously, Google Street View, more than dynamic factors, allows you to consider the average that those dynamic factors occur.
yeah, yeah. Okay. There's one again from NL. How does Cycle AI compare to Komoot, which also identifies hotspots? Do you know this company?
Commute, I'm, I don't know
Komoot.
commute, but the main point, the most central point of our approach is not the hotspot identification. There is another one. There is plenty of them that allows for this hotspot identification. We only because we only gather we only put these we only create this hotspot map as a way to validate whether these points that were manually inserted are identified as well by our model. Our main approach, the main plus of our approach is having a model that is able to process images and create safety maps without us needing the intervention of other people.
Okay. Um, Now I'm going for one of Lillian Denzler. Are there any data privacy concerns regarding the route planner app? How do you handle user data in your app? In your app?
So that's one of the main things that distinguishes from other approaches. All the data that we get from users is totally anonymized, and the data that we got from the users are absolutely only used to identify the most dangerous points, to create the neural network that identifies the most dangerous points and to build the route planner. So in that case, there is absolutely no data used for commercial purposes something that you cannot say when we talk about big tech companies like Google, for example.
Yep, for sure. Um, Now, going back to Andre, by using satellite imagery, how will you get ground truth labels? Do you plan to use the same crowdsourcing labels?
That's a very, very, very good question. So, what I believe what we are going to do at the beginning is we will have to rely in different software, image segmentation software, that is able to identify classes of structures that we had before. For example, before we identified presence of vegetation, roads, cycle lanes. With this semantic segmentation from NVIDIA, we certainly have to use different models that were trained with different data sets to identify these same classes, but in a different perspective, satellite perspective. So the first step will be still considering that these classes were identified as dangerous or not from the Google Street View, and we aim to identify these same classes not anymore from Google Street View images, but from satellite images, but still at the beginning rely on the data that we put together through the Google Street View images. Because now, I don't know if you remember this table that we put together that already tells you in terms of safety which one of these, how important are each one of these classes. And that's based on this that we only have to change how we detect these same classes now with a satellite approach, not Google Street View.
Okay. Finally, we have another question by Lillian Denzler. How computationally intensive is it to analyze satellite images in real time to improve your risk detection?
So computational leads were since the very first second central to this project. Not necessarily for YOLO v5 that considers more the object level, but especially for image segmentation that each one of the pixels is analyzed pixel by pixel. And analyzing pixel by pixel, 1 million images, the computational requirements are very, very, very high. To give you an idea, um, I've analyzed in the past something in the order of 5,000, 500,000 images, and I've made it in 1 day, 2 days, but it took me having 13 jobs running in parallel in 13 different GPUs. So this basically means that if we are doing this and with our laptops, it will take years to get these images segmented. Essentially, the image is segmented, then the objects detected, because this object detection can easily run in like small devices. For example, the prototype. But the main point is, at the end of the day, satellite images will for sure have a higher resolution than Google Street View images. But at the end of the day, it will be one satellite images will be the equivalent to many Google Street View images. So on one side, it will take us longer to analyze one, but we'll need less.
Okay. I have not one, but a few more questions from my side. I would like to know if you use any tool like MLOps, Data Ops that you would like to recommend for people that are working with a lot of data, especially uh, visual data.
What are ML ops?
Machine learning ops in the meaning that, well, it's kind of data engineering, and it's like tools that help you develop your application in the whole. Uh,
Data
so
visualization, for example, and data
data,
processing, etc.
yeah, data processing, data versioning, for example. Do you have any kind of those tools
So
at CycleAI?
in terms of versioning, we are mostly use products from Microsoft because we are in Microsoft for startups, and the support that was given to us allowed us to do it. So in terms of versioning the website, Bikeable, and the route planner. We are just using like versioning
Yeah.
control like Git to do it. But in terms of like frameworks that you could use for data visualization, data processing, etc. I don't think we rely on a specific one. We rely, yes, in those in Python and in all the libraries that are made available to this programming language, either from TensorFlow perspective to the most typical data visualization like Seaborn, Matplotlib,
Mhm.
and algorithms, yeah,
Okay.
libraries.
Yes. So just one last question. What is your time schedule to provide route your route app in other places in Portugal, like Oporto, Aveiro, Coimbra? Do you have any time schedule?
So this is a Portuguese startup. We are based in Lisbon, and that's why we are starting. We are starting by Lisbon, and most of the support that we have been getting was from Portugal and from municipalities and some of the companies that are based in the city. So that's why Lisbon was our first approach. And once we have the pilot finalized in Lisbon, um, of course, the next steps will expand to other cities within the same country because Google Street View is available, and so this is not a hassle. This is not a hurdle, but simultaneously, we are taking things step by step. At the beginning,
Mhm.
we are doing it in Lisbon. We need to, as a proof of concept in a smaller area. Once the pilot is finalized, which will be in 2 months, probably less, we start expanding to other cities, Portuguese cities, and abroad for sure as well.
Yeah. Okay. Thank you very much, Luis, for sharing all this with us. I would like to inform everyone that the video will be available afterwards for you to rewatch and share with your friends. Also, we will provide probably the slides on GitHub. If you want to provide some feedback to our sessions, please fill the form in the description. And if you want to speak at one of our sessions, please talk to us through our email. Um, Thank you, everyone, for showing up. And yes, see you in 2 weeks.
Thank you very much, guys. It was my pleasure.